Hello future engineers, welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe, press the notification bell, and if you find my videos helpful, not only to you but to your friends, then share them so that I would also be encouraged to do more lecture videos which will be beneficial to your studies. So I hope that you will enjoy watching my videos and you'll learn a lot. Okay, let's have problem 23. A steel rod with a cross-sectional area of 150 mm square is stretched between two fixed points. The tensile force in the rod at 20 degrees Celsius is 5,340 newtons. What will be the stress at negative 18 degrees Celsius? Letter B, at what temperature will the stress be zero? Use beta 11.7 times 10 to the negative 6 per degree Celsius. So this is the figure. Of course, initially at 20 degrees Celsius, this is subjected to 5,340 newtons. So if it contracts, then the stress will increase further. So it's still tension. So first, that's the force. Then we can compute the initial stress. So imagine that this is the deflection initially. So it should contract so that the stress, if it contracts, the stress will increase. So this is the final, and that is the deflection due to a drop from 20 degrees to negative 18 degrees Celsius. So from here, there's a need to stretch this, and the resulting stress is the final stress. So at 20 degrees Celsius, stress at 20 degrees Celsius is force over area, 150. So it is 35.6 megapascals tension. Then at negative 18 degrees Celsius, delta T is negative 18 minus 20. So negative 38. So it means that it should contract. So beta L delta T, or balat, so that you can easily recall it. So delta at negative 18 is coefficient of thermal expansion, 11.7 times 10 to the negative 6 times the length, let's call that L, times final temperature, negative 18 minus initial negative 20, minus initial positive 20. So by the way, the formula is written in this manner so that you can easily recall it. Most of the books in mechanics of materials or mechanics of deformable bodies, the coefficient of thermal expansion is alpha instead of beta. I'm the only one who makes this beta so that you can easily recall the formula. Or for other topics, bulk modulus of elasticity, that's volumetric expansion or contraction, that is supposedly beta. So in terms of L, it is equal to negative 4.446 times 10 to the negative 4 of L. Then displacement at negative 18 plus displacement initial equals displacement final. So let's make this positive. Displacement initial is stress 35.6 L over modulus of elasticity. So initial stress, initial deformation or displacement is 1.78 times 10 to the negative 4 L. So that this final stress will be developed, delta P should be equal to the sum of these two, and let's make it positive, the two. 4.446 times 10 to the negative 4L plus 1.78 times 10 to the negative 4L equals stress final length over 200,000. So you can cancel L and solve for final stress is 124.5 megapascals. For part B, what will be the stress? At what temperature will the stress be zero? So it should be the initial displacement, which is contraction, should be equal to the final displacement, which is elongation. So that there will be no stress at final. So that's delta 1, delta initial, and this should be the delta also due to thermal expansion delta T. In other words, the temperature should increase, not decrease like here, because if it decreases, the tensile stress in the bar will increase further. You see 35.6 to 124.5. So the temperature should increase. It should be higher than 20 degrees Celsius in order that the final stress will be zero. So this is the idea. Its stress delta T due to thermal expansion should be equal to this displacement delta I. So beta 11.7 times 10 to the negative 6 times L times delta T final temperature minus 20 degrees Celsius equals stress at 20 L over E. So you can cancel L. Stress at 20 is 35.6. So 11.7 times 10 to the negative 6 times TF minus 20 equals 35.6 over 200,000. So solving for TF in degrees Celsius, it is equal to 35.21 degrees Celsius. So that's the answer to this problem. Okay, problem 24. This is a basic problem on thermal stresses. The bronze bar, 3 meters long with a cross-sectional area of 300 mm square, is placed between two rigid walls at a temperature of negative 10 degrees Celsius. There is a gap of delta 3 mm as shown in the figure. Find the stress when the temperature is increased to 50 degrees Celsius. Use beta 18 times 10 to the negative 6 per degree Celsius or coefficient of thermal expansion for this bronze bar and modulus of elasticity E of 83 gigapascals. So this is the figure. So let's draw the situation. Allow the bar to expand. It should expand because the temperature is increased. So let us say up to there, and because this support is unyielding, as soon as it expands, it experiences a compressive stress. So this should be the final level of the bar here at this point, and this is expansion, so delta T due to thermal expansion, and this stress here will cause this end to go back up to here because that should be the final length, and that is denoted by delta due to the stress. So delta is delta T minus this gap here, which is 3 mm. So delta T is beta L delta T or balat. So delta T is 18 times 10 to the negative 6 per degree Celsius times 3000 mm, the length of the bar initially, quantity delta T final temperature minus initial temperature. So I use this formula so that you can easily recall it. So delta T is 3.24 mm. So solving for delta, which is equal to 3.24 minus 3 mm. So it is equated to stress due displacement due to stress, which is stress length over E. So 0.24 equals final stress times length 3000 over 83,000. So supposedly you can also use 3003 here instead, but the effect is very small. So delta is equal to 6.64 megapascals, and the sense is compression. That's it for this problem. Okay, for problem 25, the composite bar shown is firmly attached to unyielding supports. An axial load P of 200 kilonewtons is applied at C towards A at 20 degrees Celsius. Find the stress of segment 1 at 60 degrees Celsius in megapascals, stress of segment 2 at 60 degrees Celsius in megapascals, and part C, determine the temperature in degrees Celsius corresponding to equal stresses in segments 1 and 2. The properties of materials are segment 1, coefficient of thermal expansion 11.7 times 10 to the negative 6 per degree Celsius, modulus of elasticity 200 gigapascal, so it is steel, and area 1200 mm squared. Segment 2, coefficient of thermal expansion 23 times 10 to the negative 6 per degree Celsius, E is 70 gigapascals, area is 1200, so it is aluminum. So this is the figure, and the load is to the left, So the reaction at B is expected to the right, of course. So meaning that segment 2 will be in tension. Oh, sorry, it is also to the left, the reaction. Yes, it's to the left because the members will expand. So as it expands, it will develop compression. So let's have to the left here so that the segment 2 will be in compression. Segment 1 will also be in compression. So we allow, this is the initial junction, so we allow this segment 2 to expand due to thermal expansion, and this is delta T due to segment 2. Then from the end of this, so we have R here. That's, if that is R, this is also R, same force. Then because of the presence of segment 1, because of the compressive reaction, this will go back to this level here, and this deformation or displacement is due to compressive stress in segment 2. So that's the delta 2. That's already delta 2 because that's the compressive, that's the deformation due to compressive stress in segment 2. So beginning here, so this is segment 1. Originally, it begins with there. Then we allow it to expand. So it will increase further. And because of compatibility, this is due to thermal expansion of segment 1, so call that delta T1. And because this is the final level of the second segment, and there should be no change, so therefore this distance is should be the deformation due to stress in segment 1. So this is R plus, because that is R right, then we consider this, so this should be R. If this is R pa left, then this is 200 kilonewtons, so the reaction here to the right should be R plus 200,000 newtons. Same is true with that. So this is in compression, and this total distance here is deformation due to compressive stress in segment 1. That's it. So if we establish compatibility equation, we have delta T2 minus delta 2. So it would be this value here, and it is equal to delta 1 minus delta T1. So that should be the compatibility equation. Delta T2 minus delta 2, which is equal to this, equals delta 1 minus delta T1. Delta T2, 23 times 10 to the negative 6 times length, 200 mm, segment 2. Change in temperature is from 20 to 60, so 60 minus 20 is 40. Then delta 2 is the force in segment 2, which is R, times length 200 over area of segment 2. Area of segment 2 is 900 mm square. Then E 70,000 megapascals to make that mm, equals delta 1. Delta 1 is force, which is R plus 200,000 newtons, times length 300 over area 1,200, E 200,000. Then minus delta T1 is coefficient of thermal expansion of segment 1. Length is 300, change in temperature 40. So simplifying, that's the first term is 0.184 minus R over 315,000 equals, this is R over 800,000 plus 200,000 times 300 over 1,200. 200,000 is 300 over 1,200, or 1/4. then minus 0.1404, this last term here. So only R is unknown here. Solving for R is 16,815 newtons. So from there, we can now compute the stress in segment 1, which is R plus 200,000. Let's compute segment 2 first. 16,815 over 900, 18.68 megapascals. It is in compression. Then sigma 1 is 200,000 plus R over area 1 is 1,200, 180.7 megapascals compression. So for in answering question 3, determine the temperature in degrees Celsius corresponding to stresses in segments 1 and 2. So if the temperature still increases, then this stress in segment 2 will increase, but at a slower rate. It cannot reach or overtake this value at segment 1 here. So for these two to be equal, the idea is so that the stress in segment 1 will decrease, so the temperature should drop so that segment 2 will be in tension and segment 1 will be in compression, but lesser than this. So there's a chance that the two stresses will be equal. One is compression, the other is tension. Because if you increase the temperature, this will increase, yet at a slower rate. It cannot overtake the compressive stress of segment 1 for that case. So the idea is the temperature should drop. That segment 2 will be in tension. So this is now the figure. Let's consider the temperature to drop so that segment 2 will be in tension. The reaction there will be in tension. So I'll call that R1. So this is also R1 here. So because the temperature drops from this position, it contracts. So this is delta T1, delta T2 rather. Then this is also R1. Because of the stress due to R1, which is tensile, it should elongate greater than delta T2. So this is from this position up to that, that's delta 2. So this should be the final level for segment 2, and from this position to this position here, that's delta 2. So now let's draw segment 1. Initially it is same length. Then because the temperature drops, it will contract. So it will move to the left. So this is delta T1 from this position to that. Then because of the stress, which is 200,000 plus minus R1 this time, it is in compression. Then this from this position to this final level here, that's the deformation 1 or deflection 1. So that should be the final end. And this value here is delta 1. So that our compatibility equation this time would be, so let's equate this distance here. This is delta 2 minus delta T2, which is this, and that is equal to delta T1 plus delta 1. So the equation, this is the idea, compressive stress in segment 1 must be equal to tensile stress in segment 2. The explanation is if the temperature rises, the compressive stress in segment 2 will increase at a slower rate because of this load here. So that's why the temperature at segment, the temperature or the stress in segment 2 must be in tension, so that there's a possibility that the tensile stress in segment 2 will be equal to the compressive stress in segment 1, which will decrease if the temperature will drop. So sigma 1 stress is force 200,000 minus R1 over 1,200 area of segment 1 equals force in segment 2 R1 over area 900. So solving 200,000 over 1,200 equals R1 quantity 1 over 900 plus R1 over 1,200. So R sub 1 is 85 740 newtons. Then delta 2 minus delta T2 equals delta 1 plus delta T1. Delta 2 is stress in segment 2, which is 85,714, force in segment 2, length in segment 2 over area segment 2, E of segment 2, minus coefficient of thermal expansion in segment 2 times 200. Let us say the change in temperature is delta T, equals 200,000 minus, this is 200,000 minus R1, length 300 over area 1,200, 200,000, plus coefficient of thermal expansion delta T1, or thermal displacement 11.7 times 10 to the negative 6, 300 times delta T. Solving for delta T, before that, let's compute each. So combining delta T's and combining these values here, so the result would be delta T is positive 15.94 degrees Celsius. Since it is positive, our assumption that the temperature should drop is correct as assumed. So final temperature minus 20 equals the drop of negative 15.94. So the final temperature should be equal to 4.06 degrees Celsius. So that should be the temperature, so that the stresses in segments 1 and 2 will be equal. For problem 26, the rigid horizontal slab is attached to two identical copper rods. There is a gap delta 0.18 mm between the middle bar, which is made of aluminum, and the slab. Neglecting the mass of the slab, calculate the stress in each rod when the temperature in the assembly is increased by 85 degrees Celsius. Use the following data. Also compute the final length of the aluminum. So this is the data. So there is the gap here, and that is 0.18. This is, let's draw the free body diagram and the deflected shape for compatibility equation. Because the temperature is increased, so allow these rods to elongate as shown. So let us say this is the final drawing or final position of this rigid platform, and this is the deflection of the aluminum rod. Because it has greater thermal expansion, so it will elongate further. Then this is the final level. So in this level, because the elongation of aluminum is greater, it stretches these two copper wires, and this aluminum will experience compressive force. So if this red horizontal line is the level after expansion, so for instance, that's the level after expansion of the coppers. So up to there only. But the aluminum bar will expand up to that level there at the top. So that's the level after expansion of the aluminum. So as a result, as it hits the bottom surface of the rigid horizontal platform, it will experience compression because it should go back to the final level. So this is the thermal expansion, thermal elongation of the two copper rods. And this is therefore, because it will stretch further because of the elongation of aluminum, so this is the deflection due to the stress in the copper wire. While from this initial position to that final position, that's the thermal elongation of aluminum, so call that delta T of aluminum. Then from that final level up to the final level of the horizontal platform, that's the elongation due to compressive stress in aluminum. So that one. So call that delta of aluminum. So because the copper wires or copper bars will experience tension, this aluminum bar will experience compression. So by statics, P aluminum equals 2 times P of copper wires, or 2 times P of copper wires equals P of aluminum. That's by statics. So deflection by compatibility equation, deflection of the aluminum due to thermal expansion minus delta, then minus delta of aluminum would be equal to this value, which is delta T of copper plus delta Cu due to stress. So I hope that you can follow. It's in the figure. So delta T thermal expansion of aluminum minus the gap minus delta A of aluminum would be this distance here, net upward movement, which is equated to delta T Cu plus delta Cu. So that's it. Then delta T aluminum is coefficient of thermal expansion 23 times 10 to the negative 6 times length is 749.82. You can use 750 if you want, but I'll just use the actual length, which is 750 minus the gap, which is 0.18. So 750 minus 0.18 is 749.82. But the solution will not be affected. The answers will not be affected if you use 750. So times increase in temperature of 85 degrees Celsius, so 1.4723 mm. Then delta T due to copper is coefficient of thermal expansion 16.8 times 10 to the negative 6. Length is 750 originally. Then delta T 85. So 1.071. So from equation 1, we have 2 times stress in copper, length is 5. Stress in copper, area of copper is 500 from equation 1 equals stress in aluminum, then area of aluminum is 400. Remember, force is stress times area. So stress in copper is equal to 0.4 of stress in aluminum. So having found this relationship, we can use equation 2 this time. So stress in copper equals, our deflection due to stress in copper is stress in copper, length in copper divided by modulus of elasticity, stress length over E. So stress in copper, or deflection due to stress in copper, is stress in copper over 160 if simplified. Then equate it to uh, 0.4 stress in aluminum over 160. So that would be stress in aluminum over 400. By the way, the stress in copper is 0.4 stress in aluminum. So divided by 160 from this. And the stress in copper is 0.4 of stress in aluminum from that equation over 140. So simplifying, it is stress in aluminum divided by 400. So stress in aluminum is equal to deflection due to stress in aluminum is equal to stress in aluminum, length of aluminum original divided by E, which is 70,000, so 0.010712 stress of aluminum. So substitute here, so 1.4123 minus gap 0.18 minus delta of aluminum is 0.010712 of stress of aluminum equals thermal expansion of copper 1.071 plus deflection due to stress in copper stress in aluminum over 400. So it is stress in aluminum that is remaining in this equation as the unknown. So we can now solve stress in aluminum equal to 16.75 megapascals compression. Then stress in copper is 0.4 of 16.75. So that would be 6.70 megapascals tension. So that's it for this problem. Okay, for our last example for strains and under thermal expansion, thermal stresses, the aluminum and bronze cylinders are centered and secured between two rigid end plates by tightening the two steel bolts. There is no axial load in the assembly at a temperature of 10 degrees Celsius. Find the stress in the steel bolts when the temperature is increased to 93 degrees Celsius. So use the data in the table below. Aluminum, bronze, and each steel bolt. So notice that the length of the steel bolt is 175 plus 25 plus 25 is 225 mm. The length of aluminum is 75, length of bronze 100 mm. So delta T of aluminum thermal expansion is 23.1 times 10 to the negative 6. Length is 75 and delta T is 93 minus 10, so 0.14380 mm. Delta T of bronze is equal to 18.9 times 10 to the negative 6. The length is 100 and delta T 93 minus 10, so 0.15687 mm. And thermal expansion of steel is 11.7 times 10 to the negative 6 times length of steel 225 mm, delta T 93 minus 10. Balat, remember, 0.2185. So if you add this thermal expansion of aluminum and bronze combined compared to that of steel, so the combined thermal expansion of aluminum and bronze is greater than this. So that means that the steel should be in tension while the force in the aluminum and bronze, which is common because they just lie in one line, the transmitted force will be compression, and we will call that P. So delta, again, thermal expansion of steel is less than the combined thermal expansions of steel and bronze. So that's why the steel should be in tension and aluminum and bronze should be in compression. So we draw a line. Let's fix this. Let's say this is the any section length of steel. We allow them to expand. That's the final position. Then because these ends here are fixed, so naturally this will be in compression to return back to the original length. So we have delta T of steel, this one delta T of bronze and aluminum combined. Then due to stresses, let us say this is the final level, then the steel will elongate further. So due to the forces, tensile forces in the steel, and this deformation here is deformation due to stress, tensile stress in steel. So we'll call that delta S sub D. And this deformation here is due to compressive force, compressive stress. And that's the combined compressive deformation due to bronze and aluminum combined. So this is delta aluminum plus delta of bronze. So that's it. So P therefore is equal to 2 times P sub ST, and that P there is the force in the bronze and the force, compressive force in the aluminum, and equated to 2 times PST. So this is by equilibrium or statics. So delta TST plus delta ST, this value here, should be equal to delta TAL plus delta T of bronze, then minus delta AL minus delta of bronze. This one. So I hope we are just equating this length here. So delta TS due to steel plus delta ST is equal to delta due to temperature of aluminum and bronze combined, then minus the stresses in aluminum and bronze combined. Oh, sorry, not stresses, the deformation due to stresses of aluminum and bronze combined. So these thermal deformations are already computed. So let's transpose this negative value here. So 0.2185 plus delta ST equals 0.1438 plus 0.15687. They are computed there, minus delta AL minus delta of bronze. So transpose to the left, so delta ST plus delta AL plus delta BR equals, or by additive inverse, 0.08217. So this is equal to force in steel, length of steel divided by area of steel, E of steel. So PST, length of steel 225, area of steel 485, E is 200,000 megapascals to make it mm, and force is in newtons. Force in aluminum is 2 times PST from here. Length of aluminum 75, area 1290, modulus of elasticity 69,000 megapascals. Plus force in bronze, which is the same, 2 PST, or P is 2 times PST. Length of bronze is 100 mm divided by area of bronze, 1935 mm square, and modulus of elasticity 83,000 equals 0.08217. So it is force in steel that is left in this equation as the unknown. So computing for PST, it is equal to 15,651 newtons. So this is the force in the bolts. Then the stress is equal to force over area. So you divide that by 485, 15,651 over 485. Then we get the final stress in the steel rods, steel bolts, as equal to 32.27 megapascals tension. So that's it for this final problem. So I hope that you were able to follow the solutions and keep on practicing so that you can master problems in strength of materials. So it needs analysis and deep thinking skills. You follow the suggestions by the authors so that you will learn how to solve or attack problems on strains.